We are beginning section, part 2 of module number 2, lecture for module number 2, reading from the failed, it's going to be a day like this, famed Yale computer science professor quits believing Darwin's theory, handout. All right, in May, the Claremont Review of Books published a column by Gerlentner, headlined, "Giving Up Darwin." In it, he explained how his readings and discussions of Darwinian evolution and its competing theories, namely intelligent design, have convinced him that Darwin had it wrong. In particular, he cites Stephen Mayer's 2013 book, Darwin's Doubt, as well as The Deniable Darwin by David Berlinski. The professor expanded on his views in an interview with Stanford University's Hoover Institution that was published last week. Gerlentner stopped short of fully embracing intelligent design, both in his essay and during his interview. He said in his interview, he sees intelligence in the Earth's designs and has no quarrel with the ID proponents, but notes the world is a mess. Its suffering far outweighs its goodness. Classic argument against theism in terms of belief in God is the badness of man and the difficulties of life on earth. And I would suggest to you that that is one of the strongest arguments for the existence of God and a fallen world, a sinful humanity. But that's all right. My argument is with people who dismiss intelligent design without considering, it seems to me, it's widely dismissed in my world of academia as some sort of theological put-up job. It's an absolutely serious scientific argument, Gerlentner said during his interview. In fact, it's the first and most obvious and intuitive one that comes to mind. It's got to be dealt with intellectually. Gerlentner said an ideological bent has taken over the field of science, and that is so true. It is theoretical science that has risen to scientific law in so many instances, and especially in origins. But we see it, as I mentioned to you, in discussions about climate. Well, there he is Thomas, is that right?
Yes.
How about that? You were predicted to have been here. Welcome. You will find that, and if you will examine what you were taught, if you go on to institutions of higher learning, you are going to find that theory is often presented as fact these days. That's the current condition of science. Maybe your generation will help fix that. I pray, hope so. There are good scientists doing good work, but we have a cautionary tale in what happened to our English departments and our history departments. It could happen to us, God forbid, he said. Gerlentner said he likes many of his colleagues at Yale, that they are his friends, but when he looks at their intellectual behavior, what they've published, and much more importantly, what they tell their students, Darwinism has indeed passed beyond a scientific argument as far as they're concerned. You take your life in your hands to challenge it intellectually. They'll destroy you if you challenge it. You know what? You need one of these. Yeah. Oh, maskless. Here, could you come get it? There you go. Thank you. Now, I haven't been destroyed. I'm not a biologist. I don't claim to be an authority on the topic, Gerlentner added. But what I have seen in their behavior intellectually and at colleges across the West is nothing approaching free speech on this topic. It's a bitter, fundamental, angry, outraged rejection of intelligent design, which comes nowhere near scientific or intellectual discussion. I've seen it happen again and again, and this is a year later, and I would suggest to you again that it's worse than ever in terms of the demand for conformity to what should I say, a majority opinion on campuses. Gerlentner acknowledges I'm attacking their religion. And that's the key to this. And I don't blame them for being all head up. It's a big issue for them. Evolution and other theories, in terms of these theories that are driven as fact, really do function as the religion of these folks. It does. It plays the same role as God does in your life. It plays the role to provide meaning and authority and, in a twisted way, some kind of hope. There is no hope in molecular evolution. There is no hope because there's no God. How does the field of biology get over Darwin? Well, Gerlentner said the outlook is bleak. Religion, I'm on the second page, is imparted more than anything else by parents to children. And young people are brought up as little Darwinists. Kids I see running around New Haven are all Darwinists. The students in my class, they're all Darwinists. I'm not hopeful. But in his piece for the Claremont Review, Gerlentner pointed out that this is one of the most important intellectual issues of modern times. And every thinking person has the right and duty to judge for himself. Your worldview affixes who you are, what you do, what you strive for, who you vote for in life. It's one of the most important issues of your life. There is no reason to doubt that Darwin successfully explained the small adjustments by which an organism adapts to local circumstances. Changes to fur density or wing style or beak shape, as the professor wrote. Yet there are many reasons to doubt whether he can answer the hard questions and explain the big picture. Not the fine-tuning of existing species. We talked about that last week when we introduced the topic of theory and scientific law. But the emergence of new ones. The origin of species is exactly what Darwin cannot explain. And that is true. That is true. In his piece, Gerlentner cited the Cambrian explosion as one of the insurmountable problems facing Darwinism. That's because the fossil record shows a striking variety of new organisms, including first ever animals, pop up suddenly in the fossil record over a mere 70-odd million years. This directly contradicts the expectation by Darwin that new life forms evolve gradually from old ones to a constantly branching, spreading tree of life. It's the truth. The fossil record disproves Darwin, not proves him. What's more, Gerlentner adds, Darwin's main problem is molecular biology, pointing out advances in technology have brought forth vast amounts of new information and understanding about the complexity of life, all of which has shown random mutation plus natural selection cannot generate new and complex creatures. Virtually 100% of mutation is negative. It is deleterious to any type of organism. The idea that mutation is going to produce more advanced organisms is just myth. That's the right word. That's strong talk for a little guy here, but it's the truth. It's just myth. What's more, that's right. By the numbers, it's impossible. And this is where Gerlentner comes in. The computer scientist points out. He gives an anecdote on how hard it would be to create just one new protein by chance. The odds are so astronomical that there are fewer atoms in the entire universe in comparison. The odds bury you. It can't be done. Underscoring all that, the professor notes there are no examples in scientific literature showing that mutations that affect early development and the body plan as a whole are not fatal. In other words, the idea that random chance and mutation are the driving forces behind the vast complexity of life, even with billions and billions of years of time, is not just scientifically improbable, it is an impossibility, the scholar argues in his piece. Darwin would easily have understood that minor mutations are common, but can't create scientific evolutionary change. Major mutations are rare and fatal, Gerlitner wrote. It can hardly be surprising that the revolution in biological knowledge over the last half-century should call for a new understanding of the origin of species. Whether biology will rise to the challenge and develop a better theory remains to be seen, the professor concludes. How clearly and quickly can the field get over Darwin and move on, with due allowance for every Darwinist having to study all the evidence for himself? There is one of the most important questions facing science in the 21st century. So there you go. This is what you've been handed. You, along with those who will study with you, are like the, what was it, 16th, 15th century folks who just were convinced that the earth was flat. That's where we're at in many aspects of science. You got to look at the questions and ask hard questions. And so I wanted to pass that along to you with regards to our questions about theory, as I say, and scientific law. We began the module with them. And so I'm not going to test you over that. I can tell you there might be an extra credit question associated with that little goodie. So keep it in mind if you would. All right, we are on chapter or module 2, and we have hit all the way to calibration on page 2. Not too bad, I don't think. So, did we define calibration? I don't think we did. Let's see if it's in the back here. Probably not, because I need it to be back here. Calibration. Ooh, how about that? All right, here we go. I'm reading, you fill it in. The process of using certain physical measurements to define the scale of a measuring device. So calibration, if you'd write that on your notes, page 2. The process of using certain physical measurements to define the scale of a measuring device. So, if we had the time, we still might do this. We've got a number of different thermometers at the house. Same model, made at the same time. If you put them in the same solution of water, be it a hot or cold, some of them will measure differently than others. That's just the way flawed human things are. Some things are calibrated accurately, and some things are not, including thermometers. All right. So calibration is that process whereby you try to get it right. All right. If ice and water are thoroughly mixed, the temperature of the mixture will stay the same at 0 degrees Celsius or 32 degrees Fahrenheit, regardless of the amount of ice or water present. That's in your notes there. So, the point of that is that if you have a glass, well, there's no ice in here, but you have a cool, refreshing beverage with ice in it, and that ice has been there for a moment or two, if you measure the temperature of that, it will be somewhere around 32 degrees. Now, the exception to that, we're talking about water, is depending on the type of water that you have. If it's out of your tap, it might not quite be 32 degrees, just because you have you have other items in your water, and as we will see in later modules, that actually changes the freezing point of your liquid. But if you had distilled water, in other words, water where just about everything is removed from it, it's just pure water, if you put a thermometer in there with it and you've got ice and it's been there for a while, it will be 32 degrees. All right? So if you will remember that, it doesn't have to be a solid block of ice to be 32 degrees. It's water with some ice swirled around, sitting there for a little bit, put the thermometer in, it's 32 degrees. Guess what about the opposite? You put your thermometer in a pot of water that's been on the stove for a little bit, and you notice a couple of bubbles are coming up. Boiling water is always at the same temperature, 100 degrees Celsius or 212 degrees Fahrenheit at standard atmospheric pressure. That's another variable which we will discuss in the future. Whether it is boiling rapidly or hardly boiling at all. If you would, turn over to page 42 in your textbook. Take a second and get there, page 42, because there is a pretty picture for you. It's an illustration of what we're talking about. All right? Oh, that's good today. So, if you have your pot of water on and you notice just a few bubbles in your pot, what temperature is that? If you were guessing, what temperature is that water? Just a couple of bubbles. Say what?
212 degrees.
Thank you very much. Just a couple of bubbles, and you've reached boiling. You don't have to wait till it's all over the stove. Just a few bubbles, and you have reached boiling point. All right? So, with regards to boiling your eggs, all right, I think the recipe it's not a big deal, although I've blown eggs all over a bowl before by putting them in a hot, putting them in boiling water without first having them in the water and letting them warm up with the water. So the rule of thumb is, I think you boil them for 3 minutes. Isn't that the deal? I'm pretty sure that's the recipe. So you bring the eggs to a boil. So you don't start counting when you know, it's bubbling everywhere. When you see a few bubbles, it's boiling. And so you start your timer at 3 minutes then on. Any questions about that? Simple concepts, although kind of contrary to the way we think. You know, we think something has to be frozen solid to be frozen, for ice to be 32 degrees or 0 degrees. But no, that's not the case. So any solution with ice in it, and the same thing for boiling. Just a couple of bubbles and you are boiling. Questions? We got a few more things to do, so let's move right along. Take a look at on page 45, but your notes, I have added 2 equations for you. And they are the change from Celsius to Fahrenheit and Fahrenheit to Celsius. And you see the equation there, and let me quickly remind you in terms of what stuff is done. I can never remember the acrostic. What's the acrostic for what you do first? Somebody help the boy.
Oh, PEMDAS.
What's that?
PEMDAS.
Yeah, so say it.
Parentheses, exponent, multiply by add, subtract.
Thank you very much. Take the mask off and shout it for us, would you please? So everybody hears.
Parentheses, exponents, multiply, divide, add, subtract.
And what does that stand for again?
PEMDAS, PEMDAS.
That's right. Thank you. Did y'all hear that? You remember that? Do you hark back to the olden days of math to remember that deal? I can never remember it. It's because I don't want to remember it. Those are bad days for me, but in any respect. So parentheses is first. So you do what the parentheses say, and then you do the rest. All right? So in terms of the centigrade equation, you got Fahrenheit. They gave you Fahrenheit. So the first thing you're going to do is subtract 32 from that. All right? Then you're going to do the little bit of math. You're going to multiply whatever you get from Fahrenheit minus 32 times the 5/9. And of course, the way that works is you're going to put whatever you get, Fahrenheit minus 32, over 1, and then multiply the 9 times 1, and then the 5 times whatever you had, and then divide the 9 into that. So that's how you do that one. But look at the next one. So Fahrenheit, and I've written this down because I think the first year I taught that, I just looked at the thing and and forgot the principle. But anyway, the idea in Fahrenheit is that you multiply the 9/5 times the centigrade before you add the 32. So if you do it the other way, you're going to mess it up. So you multiply 9/5, that's whatever they gave you centigrade over 1, 9 times whatever they gave you over centigrade, 5 times 1, so, and then you divide the 5 into whatever you got, and add the 32 to it, and that gives you Fahrenheit from centigrade. All right? There's an example on the bottom of page 45. Look at it fast. The student uses a Fahrenheit thermometer to do a chemistry experiment and then must convert his or her answer to Celsius. If the temperature was 50 degrees Fahrenheit, what's the temperature in Celsius? So remember what we're doing. We're going to subtract the 50 minus the 32. I believe that gives you 18. So 18 times 5 is, I think that's 90. 9 times 1 is 9, so you divide the 9 into the 90 and you get 10. So as it turns out, 50 degrees Fahrenheit is 10 degrees Celsius. All right, so that's how you use that equation. And one more step for you. It's impossible. Remember what we talked about last week in terms of the absolute temperature scale, which is Kelvin. Kelvin is degrees centigrade plus 273.15. All right? So why do we have to have a Kelvin temperature scale? What's the big deal about that? And why would you want to add 273.15 degrees? Well, we explained that briefly last week because everything known to man and woman heads on a straight line in terms of decreasing volume and temperature. Everything known is heading towards minus 273.15 degrees centigrade. Everything we know. Now, we said last week that nothing can ever reach 0 in terms of volume, right? Because that would mean that whatever you've got is gone. It's been destroyed, and we don't do that, not in this creation. So it'll never reach minus 273.15, but it's heading there. Everything known to man. And so since it never reaches minus 273.15 degrees, that means if you add 273.15 degrees to whatever you have Celsius, you know it will always be a positive number. In other words, you'll never have a negative Kelvin temperature reading. And as you will see as we go through the course, not as much in this course, but the key is that there are some calculations that demand a positive temperature scale. And so that's why Kelvin is used. All right? So whatever you got, centigrade, you add 273.15 degrees, 273.15 to it, and you got Kelvin. So, you know, some of the questions they tell you are going to be tricky. They're going to give you Fahrenheit, and they're going to say, tell me what this is in Kelvin. So what you got to do, you got to convert Fahrenheit to centigrade, then convert centigrade to Kelvin by adding whatever you got to 273.15. Oh, no, boy. Better. Questions about that? There are some examples here, but I want to keep moving because we got some more stuff to do, okay? Turn over to page 48 in your textbook. 48. Let's define a calorie. That is the amount of heat necessary to warm 1 gram of water, 1 degree Celsius. Let me repeat that. A calorie, a chemistry calorie, is the amount of heat necessary to warm 1 gram of water, 1 degree Celsius. A fly amount of water to warm it up 1 degree. That is a calorie. It's the amount of heat or energy, we could say. But I want you to use the word heat for right now. All right? Now, as it turns out, of course, a calorie is a unit in measuring energy. And another unit for measuring energy is joules. Joules, not the Jewels. 1 calorie equals 4.184 joules. All right? It's right there in your notes. Do I want you to memorize this? Got it. You can if you want, but I just want you to be familiar with it, know where it's at in your notes, know how to convert if you're given calories and they want joules, all right? Or maybe you'll have an equation that requires an amount of heat or an amount of energy, and they give you 1 unit, but they want the other. So that is the means. That's how you convert. Okay? So, I need to burn a bunch of calories because I'm overweight right now. I am, and I need to get rid of it. So, how do I relate that calorie that I just told you about to food calories? Well, as it turns out, 1 food calorie, and I eat like 20,000 a day. No, I'm kidding. It's only 18. No, but anyway, 1 food calorie is 1,000 chemistry calories. All right? So again, what's the big deal about that? Nothing, other than I want you to be familiar with it. All right? And there it happens to be right in your notes. How about that? Isn't that helpful? And that's the case. Let's keep going. As temperature rises, an object is absorbing heat. Makes sense, right? On a cold winter day, you come in and sit down in front of a little space heater, and what happens to you? Your clothes and you start to get all toasty. Yep, that's what's happening. As the temperature in front of you rises, you are absorbing heat. All right? As the temperature decreases, an object is releasing heat. In terms of, I've got to show and tell today. Keeping my cool, refreshing beverages cool, I decided to throw one of these in the pack. So as temperature rises, this is releasing heat, and it's actually becoming warmer. It's not as cold as it was when I put it in the box. All right? So that's an illustration of that. Temperature increase or decrease, there is a symbol for that. It's called Q. All right? That's temperature increase or decrease. Q is proportional to the amount of heat the object absorbs or releases. All right? Those are statements that I first want you to understand and then to remember where you saw them and to be familiar with them. All right? Not necessarily to memorize, but to remember. All right? Now, if you would, I'm on page 49 in terms of this discussion, and now we're going to the next page of your notes. Matter of fact, it's the last page of your notes. Blessedly, it's the last page. And we do have to finish this up. Next week, I will give you a test on this material to take home, and we will review this material if you have any questions about it. Remember, we did half of this module or so last week. We're doing the other half this week. You'll work on the homework this week for it in order to be able to use that homework on the test, which you will receive next week. Then the following week you can take your time and take the test. So look at an equation that we have here. Q equals MC triangle T. Isn't that fabulous? It's a great equation, isn't it? And look what I've done for you. Because we hate the algebra, I went ahead and adjusted the equation for you. So triangle T equals Q divided by M times C. All right? Or C equals Q divided by M times triangle T. All right? Incidentally, I'm going to define those in a moment, but I just want to have a little fun with it. And then finally, if you're asked for M, that equals Q divided by C triangle T. All right? So that is the way the equation is rearranged. What in the world is it? Well, Q we just defined. That's the amount of heat absorbed or released. And so you will have homework questions and maybe something on a test that says how much heat is absorbed or released. All right? M is surprisingly, shockingly, I'm shocked. M is the mass. All right? The mass of whatever that object is. All right? C is the specific heat of that object. Now, as it turns out, specific heat is going to be pretty much a constant for each given element. All right? And as a matter of fact, I've given you and or compound. It can be elements or compounds. But I've given you the same little handy dandy table that's on page 50 in your textbook. I've given you that same table in your notes. If you are asked a question, both in your homework but on your test, C will you'll either solve for C, they'll give you everything else, and you'll solve for C and then you'll tell me what it is, or if you're not asked to solve for the specific heat, then you'll see it. It'll be given, all right? Because we're certainly not going to ask you to memorize specific heats. But see the specific heat of copper and iron and glass and aluminum. So specific heat tells you how easy it is to heat up a substance. Now, this is, well, let me do one more thing before we talk about specific heat. There is triangle T. Well, what could that be? As it turns out, the triangle is actually delta in the Greek, and it means change in temperature. And so change in temperature is simply what you have at the end. You know, right? In other words, T final, temperature at the end of whatever you're doing, subtracted, that is, subtracted by the T initial, what temperature you started out with. So the difference between the final temperature and the initial temperature is delta T. And you'll be told you're starting at a temperature of such and such, or you're ending with a temperature at such and such. Sometimes they'll get tricky and they'll give you everything in the equation, including maybe T final, and they'll ask you for T initial. So that's one more step in terms of trying to solve for this silly thing. So what you'd ultimately do is solve for delta T with the other ingredients in the recipe, so to speak, and then use what you have, what they've given you, either T final or T initial, and you've solved for delta T, the total, and then find out what they're asking you for. So there are the ingredients of this change in heat equation, measuring heat, and here is how you can relate to it. All right. Notice these ones that are given you there. Copper, iron, glass, and aluminum. So, and notice how fast those heat up. That's what specific heat is telling you. A specific heat tells you how easy it is to heat up a substance. And notice that copper's the first one. Well, interestingly enough, anybody have Revereware pots and pans at home? Anybody know what that stuff is? Maybe at your grandmother's house you've seen Revereware. So it's stainless steel on the top, and it looks like there's this little copper colored, because it's copper colored stuff on the bottom of the pot. Have you seen those pots? Anybody? Oh, we've got heads shaking. All right. We were given a set of Revereware. That was the standard when you got married 100 years ago when I got married, but actually it's about 40 years ago. But that was the standard wedding gift. There you gotta get some Revereware because it was the best stuff out there. You know, now they've got all this non-stick stuff, which is good too. But anyway, so copper heats up the fastest. That's why they put it on the bottom of pots. All right. Then notice next, iron. Anybody got an iron skillet here? Yep. It makes delicious stuff, does it not? So iron heats up pretty fast too. Glass. You cook with Corningware, you know, these sorts of things. And then finally, aluminum, all right? As it turns out, it takes more heat to heat up aluminum than it does copper. Like density, each substance has its unique specific heat. You can identify it based on that. The specific heat of water is 1 calorie per gram times degree centigrade, or 4.184 joules per gram degree centigrade. And look what's interesting over here on page 48, if you still got your book open to that. A calorie equals 4.184 joules. We got interesting numbers that line up together, don't we? So as it turns out, the specific heat of water is also very similar to the units that we're using to measure heat or energy. All right? The calorimetry equation, which is at the end of this textbook. So first year I taught this class and we've made it. We've hustled through and we've made it. First year I taught this class, I was told that the students in years past found calorimetry to be the hardest part of the class. And so it was. Turned out to be the hardest part of the class. And at least in some respects. I think stoichiometry actually is a little more difficult. I think in terms of my experience, students have had more trouble with stoichiometry than they did with calorimetry. Well, taught it through that year. Actually taught it through the next year, but noticed something after teaching it, and that is that after this module, you never see calorimetry again. So guess what I'm doing with calorimetry? Forget it. We're not doing calorimetry. So don't worry about calorimetry. If there's questions that you have done in your homework that have to do with calorimetry, well, that's great. Maybe I'll even give you extra credit for it, but I'm not going to require it of you. So if you come across questions in your textbook, need to be listening to this, need to wake up. What's he saying about homework? He's saying that if you're doing your homework and there's questions about calorimetry, don't do them because you're not held responsible. You want to read through it? Put me to sleep, frankly, but it'd be fine for you to read through it, but you're not going to be required of it for your homework or your test. All right, so we did have to hustle through in terms of the specific heat equation. And so what I will do next week is do a few examples of them before we introduce Module 3. Good morning. How you guys doing? Yeah, you doing okay? Yeah. We haven't started A&P yet, but we'll be there in just a minute. Is there anything that you need to know? Any questions? Questions at all? Alrighty, so this is what I need you to do. I need you to listen for your name, and when you hear your name, bring your homework up to me and let me see it, and bring your test that you may turn it in as well. Folks on the computer there, I think I've received your homework, Liam, and your test, so that's great. And I'm not sure about you, Jachin, but you'll need to send that along if I haven't received it. So seems like maybe I have received yours too, but in any respect. Hey guys, I've got to check homework. Thank you for Zooming. I hope it worked out. Was there a lot of glitches during this time?
There was a few.
Is there? They were supposed to have gotten fiber down here and to make it work a little better, but well, we do the best we can. And the video will be up. Well, we've just found these things to take longer than what we thought, but we shoot for Thursdays. Didn't make it till Tuesday last week, so but we'll try. So you guys have a great week.